conservative forces, and then we'll get into conservation of energy and gravitational potential energy. When we talk about forces being conservative, we're talking about what they do with energy, whether or not they conserve energy or not. And you'll need to know a couple of things. I'll write these down in just a second. But you'll need to know that conservative forces conserve energy, one. Non-conservative forces do not conserve energy. Conservative forces are path independent. Uh, that means that it doesn't matter the path that they take to get from one point to another. They're still going to require the same amount of energy to act over the beginning point to the ending point. I'll draw you a picture and show what I mean in just a second. On the other hand, non-conservative forces, they don't conserve energy. They are path dependent. So it does matter the path that they take. Friction is a good example of a non-conservative force, and also illustrates this idea of path dependency. If you imagine friction, an object going from one point to another, and there's a frictional force acting on that object as it moves from one point to another, it very much does matter the path that it takes, because that object is, if it moves over a longer path, then it has a greater distance over which the friction acts, and the amount of work that that object does is dependent upon the path or the distance that it takes. I'll write this down. I'll try to make it more clear. But you need to know that they conserve or don't conserve energy. They are path independent or they are path dependent, it means. And friction is a good example of a non-conservative force. For conservative forces, a good example are field forces. So gravity is a good conservative force, and the electric force, anytime you have a force that doesn't require contact, then it's going to conserve energy. And conversely, anytime you have a force that does require contact, that force is going to lose energy. When I talk about losing energy, I mean that it's it's producing energy that's no longer usable. So, for example, with friction, which is a good example of a non-conservative force, if I have a frictional force that acts, like when I rub my hands together, what type of energy does it lose? Or it loses energy to what? Yeah, it produces heat, right. So my hands warm up, and then that heat just sort of goes out into the surrounding environment. So that we typically talk of that as energy that's lost. It's no longer usable. It's not kinetic energy or potential energy. All right, so conservative forces, just sort of recap all that. It's a force that conserves energy. You could see a multiple choice question just asking you one of these three things. What is a conservative or non-conservative force? Conserves or doesn't conserve energy. Um, and in a conservative force, the amount of work done by the force changes the energy by the same amount. So for example, a good example of a conservative force is gravitational force. Imagine that I have an object that moves from this distance. We'll call this a height h, and it has a gravitational force that's equal to m times g. It moves through this distance down to h equals 0, so it moves from a certain height h down to the ground. The amount of work that is done on this object, work is equal to force times displacement. By the way, does the gravitational force, does it do positive or negative work on this object? Positive, it does positive work, right? Because the displacement and the force are in the same direction, so it's doing positive work. It's also increasing the energy. Remember, positive work means not a direction, but that it's adding to the energy. All right, so the work is force times displacement. That's going to be my force, which is m times g times h, which is my displacement, and it's going to be positive. The work that is done is equal to mgh. Likewise, the change in energy for the object is also going to equal to m times g times h. That'll become very important when we get into conservation of energy, this idea, and we'll also revisit this scenario when we look in the next section at gravitational potential energy. All right, so that's what it means that the work done by the force changes the energy by the same amount. That all the work that this force is doing goes into a change in energy. In this case, this change in energy is going to go all into kinetic energy. So this value, whatever it is, will be converted completely into kinetic energy. Non-conservative forces, as you might expect, don't conserve energy. And friction is a good example. The work done by conservative forces is uh, path independent. So if I imagine this object again up here, this box right here, if it goes through this path, the work that it does is mgh. But if it goes through a different path, say it starts here, and this object moves through this path like this, that is, I have this object, and I can either move it from here to here through a straight line path, or I can move it through a different path. It's still going to do the same amount of work. And that's what it means when we say that it's path independent. It doesn't depend upon the path. I think in Calc 3 you get into path-dependent forces, and we'll see a little bit of that as well. You'll do path-dependent integrals? Just you in Calc 3, huh? Oh, okay. You've already had it, or you're taking it? Yeah. All right, we'll do a little bit of this when we get into this chapter a bit more. Those are path-independent, and the work done by non-conservative forces is path-dependent. That means that with a non-conservative force, it does matter what is the path that you're taking. So imagine this: you have these two guys. They both start at the top, so they both start at the same position, and one jumps down, just straight down, and then the other follows this path along this slide. I have a couple forces. Or actually, in the first scenario where the guy's just jumping, I only have one force at work. Right? What's that force that it's acting on him? The gravitational force. That is a conservative force. It conserves energy, uh, and the work done by it is path independent. Let me pull up my notes here. Uh, in this case, the work done by gravity is the same for both of them because they're both beginning here and they're both ending at this height. So they have the same change in height. So the work done by gravity is still the same, right? That work is just equal to force times displacement, which is m times g times h, assuming that he starts up at this height, which we'll call h. So the work done by both of them is equal to mgh. The reason for that is that these forces are conservative, and these forces are path independent. So it doesn't matter upon the path, that force that acts, the gravitational force, it does the same amount of work on both, either this one or this one, even though they're taking very different paths. Now, which guy is going to be going faster when he reaches the bottom? The guy that jumps or the guy on the slide? Right, the guy that jumps will be going faster, and that's only because of the friction that's involved by the guy on the slide. Right. So this guy has a frictional force acting upon him. That frictional force acts up the inclined plane or up the slide as it is. Uh, that frictional force does positive or negative work. It does negative work. So my force is in this direction. My displacement at each point is in this direction. So the work done by the frictional force is less than zero. It does negative work. You can think then of this taking away energy. Which is just another way of saying that this is what type of force. It's a conservative or a non-conservative force. This is a non-conservative force. It takes away energy. You can think of it in that way. Friction is a great example of a non-conservative force. And again, field forces are good examples of conservative forces. They're really the only true conservative forces, field forces, because anytime you make contact between two surfaces, that loses some amount of energy. Now, in the next chapter, we'll approximate some forces as being conservative. That is, they conserve energy. Like we'll look at billiard balls and collisions, pool balls, that we'll say that those conserve energy. And they almost do, but not quite. They lose a little bit of energy. Um, all right, so then the total energy of this guy when he gets to the bottom, the total energy will equal to the work that's done by the gravitational force. Remember, this was a positive work, plus the work that's done by the frictional force. Remember, this was a negative work. So it'll have some value that's less than that. We could actually calculate it. We could say it's m times g times h minus the frictional force, which is kinetic frictional force, times the distance that he travels. Uh, Notice that the frictional force here is path dependent. So I'm going to draw this slide again. If I have this guy that goes down this slide, and there's a frictional force between him and the slide, what if he went down another slide? What if the slide instead looked like this? Which of these would have the greater energy at the bottom? Would the red slide or the blue slide? We'll do it as a clicker question. So uh, which will have the greatest energy at the bottom, the red slide or the blue slide? That is, in which scenario will the guy have the greatest energy? On the red slide or on the blue slide? Will he have the greater energy coming down the red slide at the bottom, or will he have more energy coming down the blue slide? Um, all right, just a few more seconds. I'll stop at 25, 25. Okay, awesome. A is the right answer. He'll have more energy coming down the red slide, just simply because the path is longer on the blue slide, and so he loses more energy due to friction. Right. What do you call cheese that doesn't belong to you? Don't answer, just say I don't know if you know the answer. Cheese that doesn't belong to you, what do you call it? Nacho cheese. So I told my other class that joke, and like half of them spluttered out the answer. Have y'all heard that one before? Some of you have. That's a good one there. All right. Okay, let's try doing this. We'll just remember this is just a quick dot product. So just remember your dot products. Let's try this out. I have a force that moves from R1 to R2. I just want to know how much work is done by this force. It's just a simple dot product. While you're doing that, I'm going to go down to another page. I'll come right back to this page though. All right, your first step here, your work is force times displacement, F dot D. You write out your force vector, figure out what is your displacement vector here, give you the initial and the final. sorry. All right, so have our force vector, which is 40I plus 20J plus 60K. And then I dot it with my displacement vector. Now, our displacement vector is going to be R2 minus R1. So that's going to be 32I minus 16I. So that'll be 16I. 10J minus 3J plus 7J. And then minus 12 minus 0, so minus 12K. And then if you want to do the full FOIL, although this gets pretty complicated because it has 3 terms, you can do so. But really all I have to do is multiply my I terms together, multiply my J terms together, and multiply my K terms together. Because all those other terms, those J dot Ks, I dot Ks, I dot Js, those all go to 0. So all I need to multiply are the like terms. So I have 40 times 16. What is that? 640, is that right? 640I. Oh, wait, I'm sorry. Remember, I dot I is equal to 1. So once I do that dot product, I lose all direction information. It's no longer a vector, so I don't write it as a vector anymore. It's a scalar quantity. 20 times 7 is 140. And then 60 times 12, 720. And it's minus 720. Uh, this is all in joules. I just add them up. 680, 780, 60 joules. Is that right? That's what y'all got? No. What's that? 680, 780. Yeah, I'm pretty sure that's right. You want to check your math. It is 60 joules. All right. You'll see a dot product. Like this one was just sort of thrown in there, but you can see a dot product that's more part of another question. Uh, you can find some of those like that in the homework. We'll look at some a little bit later where you'll see a problem like that. But let's move on because this is going to dovetail into conservation of energy, and then we'll come back and we'll revisit some of these things with work and doing dot products and what have you. All right, so we've already seen this a bit, but our gravitational potential energy will become important, especially when we're working with conservative forces like gravitational forces, to look at how the energy of an object changes as it moves through space. Uh, we've already seen potential energy. Potential energy describes the potential to do work. Right? We can have all types of different potential energy. We're going to look at gravitational potential energy, and then later in this chapter we'll see elastic potential energy. But you can have other types, chemical, thermal, that kind of business. Um, so if you lift an object a certain distance, you do work. So let's say that I move this object from this point up to this point. This should be delta y. Let's say that our delta y, we move it through a height h. So work has to be done to move this. That work is equal to F dot D. Both our force and our displacement are in the same direction, in the y direction. So I can simplify this just to M times G times H. Really, if you want to be particular about it, it's going to be mg times H times the cosine of the angle between them. But since the angle is 0, I'm just going to leave this off because the cosine of 0 is just equal to 1. All right. So now this object, you've moved it, you've applied a force to it, and it has potential energy. So this work causes a change in energy, and we call this energy potential energy. That potential energy will be equal to m times g times h. So this is our expression for gravitational potential energy. And we'll use it to do a lot of what we did in previous chapters, like our kinematics chapters and our Newton's laws chapters, our laws of motion. We can use it to figure out how fast something is going at particular points in its trajectory. In fact, it turns out to be a lot easier to do so. Let's see what we have here. let's do conservation of energy. So that gravitational potential energy fits into our conservation of energy like this. Conservation of energy just says that in a closed system, and here I'm defining a closed system as being a system in which energy neither leaves nor enters. So you can think of it as a box, and there's no energy going into the box. There's no energy going out of the box. Closed systems are actually pretty common, right? I mean, you can even think of your body as a closed system in a sense. You do have energy that leaves your body, but for the most part, it's a fairly closed system. It's just not that much energy. Okay, so in a closed system, the total energy is constant. I know I'm not supposed to use this word, obvious, but I mean, this is sort of a circular definition, right? That in a system where energy neither comes nor goes, the total amount of energy is constant. It's by definition constant, right? Because it's a system where energy doesn't come in or leave. And so that total amount of energy has to remain the same if you're neither adding nor taking away energy. So in an equation form, this looks like this. I just say that my EI is equal to EF, that my initial energy is equal to my final energy. And we would, just talking about kinetic and potential energy, we'd write it like this. Our kinetic energy initial plus our potential energy initial equals kinetic energy final plus potential energy final. And remember, our kinetic energy is 1/2 mv squared, and our potential energy is mgh. Let's do an example here. You have something like this in your homework. You'll see one like this on your test. You probably will have an added caveat to it, and we'll go over that later, where you have friction applied. Let's look now where we just have an object that is moving along a frictionless track, and we want to know its velocity and its height at particular points. May I move down from here? Yeah. Okay, so I have this, it's like a bead on a wire, or you can think of it as a roller coaster on a track. But I have this object that moves along this path, and I know a couple things about it. I know its mass is 100 kilograms, the acceleration due to gravity, and I know that down here, the velocity is 10 meters per second. I also know that up here, that v is equal to 0, so it comes to a rest. And then I want to know a couple things about it. I want to know what is the velocity here, or excuse me, what is this height h? I also want to know what is the velocity at half that height, and then later I want to know what is the velocity here at this point. So I want to know the answers to those three questions. In your book, actually, I think this is labeled as point C. Yeah, what is the velocity there? What is the speed? All right, so whenever you encounter a problem like this, what you always want to go into this knowing is that the velocity, or excuse me, the energy remains constant. Because I don't have any non-conservative forces, I only have conservative forces that are acting, my energy will remain constant. So whatever energy I have here, I'll also have here, I'll have here, and I'll have here. I have the same energy at every point along this path. The same is true, by the way, if I have something that's moving in a 1D path, like if I have something that I just throw up and then it comes back down to me, the total amount of energy that it has here is the same as it moves all the way through its path. So if I want to know the height h, I ask myself, well, what energy do I have down here? Well, I'm either going to have potential energy, kinetic energy, or I'll have both. Likewise, over here, I'll have potential energy, kinetic energy, or I'll have both. So at the bottom, at that initial point, at h equals 0, which do I have? Do I have potential energy? Do I have kinetic energy? Or do I have both? I only have kinetic. And the reason is that the h at that point is equal to 0, the height, and so there is no potential energy. By the way, this potential energy, this won't really come out much, but the potential energy is sort of, all right. So initially our potential energy is 0, we have kinetic energy. What about up top? Do we have potential energy, kinetic energy, or both? I only have potential. The reason I know that I only have potential is because that the speed goes to 0. So my potential energy goes away, or excuse me, I'm sorry, not potential energy, my kinetic energy goes away. Don't you wish you had an eraser like that on your paper, a control Z button? Just erase pencil marks. All right, so my kinetic energy goes away and I just have potential energy. When you see these problems, you'll just want to sort of go through and ask yourself, what is the potential or kinetic energy? By the way, at h over 2, I have both. I have both potential and kinetic energy. Neither one of them goes to 0. And down at point C, I only have kinetic energy, no potential energy there. All right, so then I can uh, begin to set these energies equivalent to one another. So at point A, or for part A, I'll set the energy here equal to the energy here. So that'll look like this. I'm going to write it out completely. Initial. Uh, in this first part, my potential energy was 0. In the second part, the kinetic energy was 0. And then I just sub in my 1/2 mv squared equals mgh. My masses cancel. So what that means is that it doesn't matter what the mass of this object is. It could be 10 kilograms, it could be 1,000 kilograms. It's still going to have the same speed when it gets up, or it's still going to go to the same height. I'm looking for h, so I'll just solve this for h. h, divide both sides by g. It's going to be gv squared over 2. That's 10 meters per second squared. 10 meters per second over 2. So that's 50 meters. So this object goes up to a height of 50 meters. Is that right? I don't know. I did it completely wrong. I'm sorry. Let me just erase that. I didn't think that sounded right. All right, I'm looking for h, right? 1/2 v squared over g. So that's 1/2 of 10 meters per second squared over g, 10 meters per second squared. That's half of 50 over 10, 5 meters. That makes more sense. We've worked this problem before, right? We've worked this problem where we have an object that we throw up with a speed of 10 meters per second, and we figure out, well, how high does it go? I know the velocity at the top goes to 0, so I can find the time that it takes to get to the top. Um, or I can do this, where I just say the kinetic energy at the bottom is equal to the potential energy at the top, and I find that it travels to a distance of 5 meters. It's a much easier way to work a problem like this than going through the whole business with the kinematics and all that rigmarole, which is a 2 or 3 step problem where you have to find the time, and then the height that it goes to the top of the trajectory. But it's a much easier problem to say my kinetic energy here has a certain amount, and then that's going to equal the potential energy at the top. And then you can solve for that height that it goes to. All right, so it goes up to a height of 5 meters. In the next part, then I want to know what is the speed when it goes to 2.5 meters, h over 2. So I say potential energy initial. I'm going to redraw this. I'm looking for here, h over 2, which is 2.5 meters. I'm going to treat this as my initial state, and this is my final state. So PE initial plus KE initial equals PE final plus KE final. That's going to be, this goes to 0. That's my potential energy plus 1/2 mvf squared. I can cancel out all my masses. I just divide through by m, so the mass becomes irrelevant. And I can solve for Vf. So I'm looking for Vf. That's going to be 1/2 vi squared minus g h over 2. Multiply this whole thing by 2, and then I take the square root. If it makes you feel better to put in numbers, that's fine. Half of vi squared, vi was 10, so it's going to be the square root of 50 minus 25 times 2, square root of 50, which is about 7 meters per second. 7 squared is 49, so about 7 meters per second. So I can find now the speed at this height when it comes up onto the first hill at this rate, h over 2. And then I also ask, what is the velocity at point C, which is this point? You should be able to tell me that without even looking at it. What is the velocity there? Without even putting your pen to the paper. It's going to be 10 meters per second. Why is that? Why is it 10? Why the velocity at point C is 10 meters per second. Why? Right, so if I think about this in terms of the energy, I say kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. At the initial state, which is here, this is my initial, this is my final. They both have no potential energy, so they're all going to have kinetic energy, so they'll have the same speed. This is also the example when we throw this thing up and it comes back down. Just before it hits your hand, when it comes back down, it has the same speed with which it started. So 10 meters per second, because it's returning to the same height. Okay. Let's do another problem, similar but different. I have a video for this one. Let me pause the thing. This is real, this is not real, this has been staged. It's probably been staged, I'm not sure. At the next basketball game, I think the cheerleaders are going to try it out. You have any cheerleaders in here? We don't, do we? No? Okay. But whatever, it doesn't really matter if it's real or not. But let's look at this. This is a problem actually that we've worked before. As I said, this a 1D motion, just throwing something up and having it come back down again. But again, it becomes a lot easier to work when we look at it from an energy perspective. So first, let's just draw a picture. Here's my basketball goal. Uh, Here's the young lady. She goes up, comes back down, hits her head on the goal, on the hoop or whatever, and then those guys catch her, and then they're all congratulating themselves and stuff for all that they did. But anyway, a couple of things about this. I can estimate. I know the height of the goal. How high is the basketball goal? How many feet? 10 feet, right. So we'll say that's 3 meters roughly. And then it looks like she goes about twice as high up. So I'll say that she goes up to 9 meters. Any estimates on her mass? Wha How many kilograms? That's what I thought too. That's pretty small, but she's pretty small. So about 50 kilograms. So she has a mass of about 50 kilograms. And that's really all we need. In fact, we don't really need to know the mass because as I said, the mass cancels out. But in this first part, I ask what is her total energy at the top of the trajectory. Now, at the top, I only have potential energy. In the middle, I have potential energy plus kinetic energy. And then at the bottom, I only have kinetic energy. So at the top of her trajectory, her total energy would just be potential energy, which is going to be m times g times h. All right, so go ahead and find out our total energy, and then once you move on and work part two of this, I'll give you a couple minutes to find the velocity at the bottom of the trajectory right after she leaves the guy's hands. So find her potential energy at the top, and then I want you to find her speed when she leaves the guy's hands, part two. Oh, not 9 meters, I'm sorry, I did 6 meters up here. 9 meters, that'd be really high. We're going to do 6 meters. Y'all, anybody have an energy for me? You got it, Sydney? 3,000 is right. So I just 50 kilograms, 10 meters per second squared. H was 6 meters. That's 3,000 joules. How about a speed at the bottom? What was her speed as they threw her up in the air? Do I have it for me? Claire, do you have it, the speed? No? Casey? Beans? No. All right, I'll give you a couple more minutes. Remember, total energy is constant. So she has 3,000 joules here. She has 3,000 joules here. And she has 3,000 joules at the top. The total energy remains constant. Okay, that sounds about right. Y'all agree with that? 11-ish? All right, so way I do this is I can do it a couple different ways. Since I know the total energy, I'll just say 3,000 joules is equal to the kinetic energy 1/2 mv squared. I don't have to do it this way. I'm going to do it a different way in just a second. Uh, that's equal to 1/2 of 50 v squared. That's 6,000 divided by 50. Root of that, which is approximately, or 6,000 divided by 50, which is the square root of 120, right, which is about 11. 11 squared is 121. But look, I could have done this another way. I was only able to do it this way because I knew our mass. I could have also just said Well, the kinetic energy at the bottom equals the potential energy at the top. That would be 1/2 mv squared equals mgh. Masses cancel. And then I solve this for v. Which is the same as what I did over there, but it becomes the square root of 2 times 10, which is 20, times 6, 120, which is 11. That's probably the easier way to do it, and most of the time you won't have the mass, so that'll be the way that you have to do it. I only did it this way because I had the mass. All right, now I also want to find their speed when she travels through the basketball hoop. The way you're going to set this up is you'll say, well, the kinetic energy at the bottom is equal to the total energy at the hoop. And you want to ask yourself, what kind of energy do I have at the hoop? And what do I know about it? So go ahead. Yeah, I have kinetic and potential energy. So go ahead and work that out. Uh, you're going to have both kinetic and potential. I know the height of the hoop is 3 meters, 10 feet roughly. Or 3 meters roughly, 10 feet. Do I have a value for me? Yep. I'm going to go and start putting in some numbers here. I'm solving for V hoop. So a V hoop, you might solve this a little differently than me. That's fine. V bottom, we found that was what? 11? Was it 11? Yeah, so we have a half of 11 squared. It's 121. Uh, Minus 10 times 3, because it's 3 meters, times 2, the square root of all that. What'd y'all get? Ready? Okay, yeah, about 8 meters per second. All right. You definitely have a problem like that on the test. I might throw a little curveball into it, and we'll look at this next time. Let me show you how that might change a little bit. So let's say that I have something like this. I mean, similar to the track problem that we have, but you see that they work out very much the same way. Um, you'll see something like this in the homework, and you can see something like in the old test, and you might see something like this on our upcoming test, which is, by the way, when is that test? The 21st of October. Is today the 6th? Oh, today's the 7th. Yeah, so that's 2 weeks from today. All right. Likely it will cover this chapter, the next chapter on momentum, and the next chapter on rotation. Okay, where was I? Oh, so You could throw a little curveball into this where I have an object that has a certain speed, and I want to know how high does it come up here? What is the height that it comes up here? But think about how the problem will change if I add a little stretch of friction. So what if I have a little stretch where I have friction? And then you have this extra thing where I'm losing energy due to the frictional forces that are at work. So we'll deal with that next time. We'll work through a problem that's similar to that, or you have a problem in your homework as well. But this is where you have to figure out, well, what is the work done by this friction, F times D? And you have to ask yourself, well, how far does this thing go before it loses enough energy to stop? Okay? We'll see that it's a little complication on this problem, but makes it a little more difficult, but not terribly more difficult, just a little bit more. Let's use the last few minutes of class. We'll do some clicker questions. We'll come back to this one next time. It's kind of fresh, but we'll wait till next time when it's not. Let's look at some of our concept test questions. I think we've done some of these, right? Where did we leave off? 5.12. Awesome. This one? Okay, so you and your friend solve a problem about a skier going down a slope starting from rest. But you choose different levels for y equals 0. Remember we said that that potential energy is sort of a relative thing. Uh, you choose different levels for y equals 0. Which of the following quantities do you agree on? The skier's potential energy, the skier's change in potential energy, or the skier's final kinetic energy? We're sort of all over the board here. I'm working a problem where I have a skier going down a ski slope. Assume no friction. Assume that he starts at a certain height. But you and your friend choose different levels for h equals 0. Like you might choose, which is sort of more standard, h equals 0 here. But your friend might choose instead h equals 0 up here. That means that when he drops down below that h equals 0, he's now going to have negative potential energy. Okay, so when I ask yourself the question is, what will you agree upon? Because there are still certain things that will not change in this. What is the skier's potential energy? What is the skier's change in potential energy? And what is his kinetic energy? I'm going to stop at 145. Okay, Rob, you put B. The answer is actually E. Now the kinetic energy, I think it does seem somewhat clear that the kinetic energy is what it is, right? Because this guy is going to have the same velocity no matter how you work the problem. Uh, However, the skier's, so definitely his kinetic energy will be the same, but also his change in potential energy will also be the same, uh, because his change in potential energy is actually related to his kinetic energy. So the change in potential energy will equal my final kinetic energy. So his change in potential energy will also be the same. Listen, we're not going to see that sort of thing very much. You're just going to use the ground as your h equals 0. But if you see this in other contexts, you might see it where you have different levels for h equals 0. And then that affects sort of how you work your potential energy. So the answer here was E. Two paths lead to the top of a big hill. One is steep and direct, while the other is long and less steep, twice as long but less as steep. How much potential energy would you gain if you take the longer path? So imagine you have a mountain. You have one path that goes straight up the mountain. You have another path that sort of meanders up to the top. How much potential energy would you gain if you take the longer path? It's twice as long a distance. This is last one, folks. I'll stop at 50. Stop at 50. Okay, it is same uh, because I have the same beginning height and the same ending height, and so the potential energy is just mgh. All right, folks. Sorry it's a little late, but y'all have a great day. Okay, I'll see you on Friday. I did send out a quick little survey. If y'all could take a look at that. If you've had class in Pelcher 240, that's one of the big classrooms that we often use for physical science classes in Pelcher. If you've had a big class over in Pelcher, if you've had any class in Pelcher in chemistry, physics, or geology, you've probably had it in that room. So if you could do that survey, it'd be great.